Hello, everybody, and welcome to another science lecture, I guess, from the Maston Public Library. Normally, Julia would introduce me, but she's actually at the library today, so I'm introducing myself. What I'm going to talk today about is the original topic is how you can have different colors of the moon, but I'm going to talk more about colors in the sky and how that's affected with things. So when you typically look at the moon, if you look at the moon in the night sky when it's high overhead, it will often look a kind of silvery gray. It might look a little bluish. It might look a little purplish or reddish, but most of the time it's just gray. And if you look at the moon when it's low in the sky, so when it's near the horizon and just rising, you'll notice it might look red and or orange, and it looks larger, for example. Part of that is due to the way our brains work, and part of that is due to the way physics actually works. So one thing to keep in mind with the night sky is if you said, what color is the moon actually? Like, what actually is the color of the moon if you could see it in its true color? And most people would probably say a kind of pale gray, because that's what it looks like in the night sky. The color of the moon is actually much darker. The color of the moon is actually closer to asphalt. So if you go out into a parking lot, I'm going to let one other person in. Connecting to audio. So hello, Elizabeth. This is being recorded, so if you don't want to be seen, keep your camera off. Otherwise, welcome. So we're talking about, like, what is the real color of the moon? And it's really close to asphalt, actually pretty dark asphalt. And the reason it looks gray, the reason it looks light gray, is because it is seen against an almost perfectly black background. And one of the things that our eyes do and our brains do is adapt what we see to match kind of the ability to see different information. So you'll notice sometimes that if you have an object and you look at it under fluorescent lights versus sunlight versus other things, it'll look different colors. You know, it can be hard to see exactly what the color is. There's even a thing, and you can see these in illusions, where you take something that looks, say, yellow in one part of a picture, and if you take that and put it over into the shadow region, it looks blue. Some of you might remember the, what was it, the dress that people said, is it black and gold or is it blue and white? And it depended on how your brain perceived that. So a lot of things that we see in our everyday lives, they are not necessarily what's actually the color in terms of a kind of scientifically measured color. We perceive colors relative to the other colors around them and depending upon what light there is in the environment. Now that's very useful if you're walking around on the earth. You know, one of the things that makes it very useful to see colors is it allows us to see, for example, fruit that's ripe. It stands out. You know, there are things where color actually helps us distinguish things, but that means that our brain kind of accentuates that in order to help us distinguish things. When you're looking at things in the night sky, or just in the sky in general, it's harder to see what that color is. So when you see something that's the color of dark asphalt, like the moon, against a deep black sky, it looks gray because it's lighter than the dark sky around it. And so that's why the moon looks rather bright and gray. So part of that is, you know, dependent upon our brains fooling ourselves, that we're not getting the full information. But there are things in which the color of the moon can change because of what's happening around it. And probably the most common case is when you see it as kind of a deep orange or reddish color near the horizon. And in that case, the fact that it looks larger is a trick of your brain, but the fact that it looks orange or red is not. It actually is orange or red. And the reason is because when the moon is on the horizon, it is going through a whole layer of atmosphere to get to you. So if you think of the Earth and you have the air around it, when the moon is low on the horizon, it has to come into the atmosphere at a shallow angle to reach you. When the moon is high overhead, all it has to do is come through the thin layer of the atmosphere. And if you think about how thick the atmosphere is, a good visualization is to imagine if you held an apple and imagine that the Earth was the size of an apple, the thickness of the skin of the apple would be about the thickness of the atmosphere. So when the light coming from the moon is directly overhead, it's not really going through much air. But when it's going shallow, really close to the horizon, it's going through lots and lots of air to reach you. The reason that changes the color is because one of the things that happens when light goes through air is that it gets scattered. So you look at, light that's scattered by various things. The atmosphere itself, even though it's clear, scatters light, but it scatters a light in an interesting way. There's this process where light scatters off of air molecules, and it's called Rayleigh scattering. And what that means is that when light comes in, the amount that it's scattered depends upon what color it is. In physics, we would say what wavelength it is. But what it means is that light coming into the atmosphere, if it's blue, it's scattered a whole bunch. And if it's red, it's not scattered. So red and orange is scattered very little, but blue is scattered a lot. This is why, for example, the sky is blue during the daytime, because the sunlight comes in and it's scattered in all different directions when it hits the atmosphere. And that's why we see this blue sky. Well, if you have the moon low to the horizon, the light that's coming in, which is basically gray, as the light comes in, the blue light is scattered in all directions. The red light really isn't, and so it actually reaches you. So what you get is you are more likely to see red light coming from the moon than you are blue light. And that's why the moon will look orange or red. It's the same thing with the sunset. If you look at a sunrise or a sunset, you'll see the same type of thing where the sun looks orange or red when it's really low to the horizon. And it's exactly the same reason. And do not stare at the sun in any sense, but when the sun is overhead, the light coming in looks fairly white. It looks, kind of a bright yellowish white. And that's because it's not going through much atmosphere. When it comes low to the horizon, most of the blue light is scattered, and what's left is the orange and red light that isn't scattered as much, and that's why the sun looks orange and red. So this is why when you see on the Earth, sunrises and sunsets have an orange sun. The moon looks orange when it's low to the horizon. There are although cases where the moon can take on a different color. One that's talked about is, you probably heard the phrase, once in a blue moon, to mean something that's very rare is once in a blue moon. And most of the time you won't see a moon that's blue. There are times when you can though, and that's usually when there is some type of dust in the air. So one of the things that happens is that dust will scatter light too. But dust has a different type of scattering. It's called me scattering or my scattering. I'm not sure on the pronunciation. But because dust is particles, when it scatters light, it's not just scattering off of atoms, it's scattering off of a surface. And so what happens is, instead of blue light being more scattered than red light is scattered more than blue. So what happens is that if you have dust between you and your view of the moon, what you can get is the light going through the dust. Well, the red light is scattered a lot in all different directions. The blue light isn't scattered that much, and so you see a blue color to the moon. The interesting thing about that is, in the late 1800s, there was a very large volcano called Krakatoa. It was the largest volcanic explosion that had ever happened. And when Krakatoa erupted, it threw so much dust and so much material into the upper atmosphere that there were brilliant sunsets, and temperatures across the globe actually dropped slightly because there was so much dust in the sky. But one of the things that would happen is that because you would have dust in the sky, you could see the moon coming through the dust and it would look blue, hence a blue moon. And so people would remember this striking blue moon that didn't normally happen before. And after a year or so after the eruption, it didn't see it again. And so once in a blue moon was this rare thing where you would only see it very rarely. So that's kind of that different light scattering is why you can get different colors of the moon. But where it gets kind of interesting is if you imagine what would things look like on another planet, you know. One of the reasons why our sky is blue is because much of our sky is made up of nitrogen, which scatters blue light really, really well. And so that blue sky that you see is because we have a nitrogen-rich atmosphere. Well, other planets that would have different types of atmospheres, the light would scatter differently. And so you would get different colors in the sky. Now, you can imagine kind of what that might look like, but we actually have one really good example of a different atmosphere on a different planet, and that's Mars. So people haven't been to Mars yet, but we have sent robotic probes, and they have really good cameras. So we know what the sky looks like on Mars, and we know what, for example, sunrises or sunsets can look like on Mars. What's interesting is that Mars doesn't have as thick of an atmosphere as Earth, and its atmosphere is mostly carbon dioxide. Carbon dioxide doesn't scatter blue light particularly well, and so you don't have the same blue sky on Mars that you would on Earth. So if you look during the daytime, mostly what you see is a kind of pale tan sky, which is, if you've ever seen the photos of Mars, you'll see this kind of reddish surface, and you'll see a pale tan sky. Part of that is because of the way we take pictures, but part of that is because that's actually what it looks like. The surface of Mars, if you look at the coloring of Mars, its real color is mostly around the area of kind of powdered cocoa. So it's a deeper brown color because it's very oxidized like rust. It looks paler when it's illuminated by light, but it's given that more reddish color because of that kind of tan sky. What's interesting because of this is that when you look at the scattering from the atmosphere, there isn't a lot of color scattering from the atmosphere. But when you have dust in the air, and dust can happen more in the atmosphere of Mars than it can here because there's less gravity and dust can stay up more, what you tend to have is not red sunsets, but blue sunsets. So because what's happening is the light from the sun is scattering off of dust, not off its atmosphere. And when it scatters off of dust, the red light is scattered more and the blue light is scattered less. So if you looked at a sunset on Mars, it's typically more blue. If you've ever seen the movie The Martian, there's a scene of a sunset and they didn't get it right. It should have been blue, and they just kind of left it kind of pale brown, which, you know, is a bit disappointing for a science person. But if you look on that link that I showed you on my website, you can actually see a contrast between an image on Mars and an image on Earth. And they are both sunsets. The one on Mars was taken by one of the rovers. And that's an actual real color picture. So when you see that bluish sky with the blue sun at sunset, That's actually pretty close to what it would look like if you looked at it. If you could stand on Mars and watch a sunset, it would look blue. Whereas if you see a sunset here on Earth, it looks red. And so those different colors that you can have are really a factor of how it interacts with the air and how dust and atmosphere can actually scatter it. It's one of the things that really in only probably the last 20 years that we've really been able to do good, accurate pictures of what things actually look like. So if you remember even pictures of things like Jupiter and Saturn and other planets, most of the pictures that we see are what we call false color images, because what most spacecraft take pictures of is they don't take color photographs. If you look at like the camera on your cell phone, it takes a color photograph. And the reason it takes a color photograph is because the sensor in your camera has all the little color sensors. It takes directly a color photograph. What spacecraft cameras do is they take black and white photographs that are sensitive to different wavelengths, because what they want to do is they want to gather in as much information as possible. So to create a color image, what you have to do is to say, well, this is the light we saw in red wavelengths, and this is what we saw in green, and this is what we saw in blue, and we can mix them all together and make an image. But a lot of times you'll make an image that looks pretty as opposed to being accurate. And so sometimes this is called the National Geographic effect, because when back when the National Geographic was popular, they would take space photographs with enhanced red. So the red would be really bright, so it would pop, and it would look great on the cover of a National Geographic magazine. It's not exactly how it looks, but it's great for selling magazines. So that kind of false color image is very popular. There are also sometimes when we use a false color image in order to see other features, things that our eyes normally wouldn't see, but you want to be able to look at it. So I do a lot of things with radio astronomy. We can't see radio waves, but we can make an image of the light that we gather in radio light and give it colors of red and blue and green, and then we can see what a radio object would look like. So getting a real accurate photo is sometimes difficult. But that's why you get the different colors. It's because of the way light interacts with our atmosphere. And if you were on a different planet, it would look in a different way. So are there any questions on that? If there aren't, I'll talk about another topic really quickly because it's kind of cool. But if nobody has any questions, okay. Well, what wasn't part of the topic, but I will talk about it. Oh, could there ever be green or purple suns or moons? Okay, that's a really good question. Let's start with, could there be a green sun? Okay. When we look at colors coming off of something, particularly the sun makes light. And so in order to have a green star, for example, or a green sun, we would have to see light mostly coming in green wavelengths and not in others. Well, here's a problem that we have. Our sun, if you look at the wavelengths and the different colors of what it actually gives off, most of the light that it gives off is around the green. And so in some sense, our sun is a green sun. So why doesn't it look green? Well, because our eyes have adapted to sunlight. So when we look at all the different light coming from the sun and scattering off of the world around us, it just says, oh, that's just light. So anything that's really bright in the green, the way our sunlight is, it just says, oh, that's just kind of white. So because of the way our eyes work, you can't have a green star because it mostly gives off green light the way a sun does for heat. it looks like a white star, like our sun. You could have a purple sun or a purple star. This is with really large stars that are much hotter and much brighter than our sun. And they typically look bluish purple, but you can see them. And in fact, if you look in the night sky now, really, if you look at the constellation of Orion, which has 3 stars and kind of a belt that's fairly easy to find, one of the stars in one of the foot, called Rigel, is a blue star, as opposed to the one in the shuttle, which is Betelgeuse, which is a red star. So you can see purple sun or purple stars, but not green stars. Could you see a purple moon? If you had enough scattering that even scattered most of the blue light, you might see a purple moon. It would look bluish purple. So for example, if there was a lot of dust in the air and it's low to the sky, so the red scattering is going away, but also a lot of the blue scattering, you might see a purple-ish sky. But related to this, if you remember the fires in California earlier this year, if you might have seen some of the pictures around, and it was in the middle of day, but it was this deep red color. That's exactly because of all of that smoke and dust that was in the air. It was scattering all of this light to the point that you would just have this red glow during the middle of the day, which looked very strange. So that's, I hope that answers your question about whether you can see a green or purple sun. Any other ones? Okay, well, if not, I've added another link. Oh, how many other color suns and moons are there? Well, in terms of stars, there's everything from deep red stars, called small red stars that are called red dwarfs, all the way up through orange, white kind of stars like ours. Blue stars, they're typically called blue giants, are kind of the range of colors. So you can kind of see bluish stars and reddish stars in the night sky. In terms of our moon, it's mostly red and sometimes blue. Sometimes they assign other colors to them, but that's not typically what you see. You can see a kind of orange moon during an eclipse when the Earth passes between the sun and the moon. So you can sometimes see that. Other moons have different colors. So moons are on other planets can have different colors, and they could be all sorts of things. But we haven't seen them while standing on another planet. But those are kind of it. We're limited in what we can see. We kind of see, mostly our eyes want to make things kind of the middle white pale color. So we see kind of red-ish or blue-ish because when we see the moon, that's what we have. Okay. Well, if you don't have any more questions on that, I added a link, and this is to a website called Earth Sky. Again, perfectly fine for kids. It's about how to see things in the night sky. And the reason I wanted to bring this up is because later this month, there is going to be what is called a conjunction with Jupiter and Saturn. So one of the ways you can tell planets are different from stars is that stars twinkle and planets don't typically twinkle. Also, the brightest objects in the sky are typically planets. So if you look out in the night sky just after sunset, and you look in the west just after sunset, you will see what looks like 2 bright stars. And one of them is actually the planet Jupiter, and that's the brightest one. And another one, which is a little bit dimmer, is actually Saturn. Okay, so if you go out, even any clear night around now, you will see in the west, just above the horizon after sunset, you will see these two planets. If you watch them over time, over the next couple of weeks, these two planets are going to appear to get closer and closer together until on December 21st, they will be extremely close together. They will be so close together that if you have a pair of binoculars or a small telescope, you could actually see both of them in the same field of view. So they're going to be a fraction of a degree apart. It is the closest conjunction, the closest these two planets have appeared to be since the time of Galileo. So you basically have to go back to the Middle Ages to get one that's this close. Conjunctions can happen all the time. Obviously, the two planets are not close together actually. What they are is, one's farther away than the other, but they happen to line up so that they look very close from our point of view. And so if you get a chance to see this, it's actually a pretty cool thing. You can see two planets in the same area just before sunset. So, but they will be closest on the 21st. So on the first day of winter, that's when you'll see these two stars. So, and it's probably fitting that it's around the Christmas holiday, because one of the ideas for the Star of Bethlehem is that maybe there was some kind of conjunction like that astronomers said, oh, that's going to be the Star of Bethlehem. Nothing specifically has been nailed down, but that's one of the ideas. So if you have a chance to check out the conjunction with Jupiter and Saturn, definitely go check it out. And if you have a pair of binoculars or something, try and look at it, because it's cool. It will be really cool to see two planets in the same field of view. It's something I haven't done, and I've looked at a lot of different things. Any questions on that? Okay. Well, if not, that's all I have today. Like I said, the library director, Stacy, is already asking me about another possibility. So in January, I'm sure there will be some talk about something. I don't know what, but if you have ideas or something you want to do, just let me know. And you're very welcome. I'm happy to do these. If you have ideas, by all means, contact Stacy and let her know what you'd like to hear about, and I will do my best to talk about them.
Okay.
Thank you, Brian.
Absolutely, you're very welcome. If there's no other questions, I will stop the video.
Yep. See you in January.
Yep.
Okay.